there's no problem in life or cosmochemistry that cannot be, if not solved, made less of a problem by an Excel spreadsheet.
You're listening to The Cosmic Cast. Hello, and welcome back to another episode of The Cosmic Cast, brought to you by the Earth and Solar System team at the University of Manchester. This week, we're joined by the regular co-hosts of Tom Harvey, Marissa Lowe, and Ricky Bahir. And we've got a very special guest for you all this week, Dr. Tim Gregory. How's it going?
Yeah, thank you for having me. It's
a
exciting
pleasure.
To be here.
Absolute pleasure.
It's great to be back with the Manchester crowd.
That's right. So you did your masters at
I did
Manchester?
my whole undergraduate in Manchester. I started in 2011 as an 18-year-old fresh from A-levels. Did the geology with planetary science 4-year course. So, I'm from West Yorkshire, but I always like to think of myself as made in Manchester.
I'm sure that's quite a controversial statement on some
Yeah, I know. They don't let me back home now.
Yeah.
So
My blood is boiling right now.
And it's even better to be here as well with Ricky, because we were undergraduates together. So we go way back.
Yeah. It's nice to have someone we've had the same trajectory, did a PhD, postdoc, someone you can relate to in that way is really nice.
Yeah, absolutely. There's nothing like a bit of adversity to forge a friendship. And we spent many hours in the Scottish hills in horizontal sleet on field trips as undergraduates. So,
Sure.
Yeah, it's good to see you.
Yeah, you too. Yeah.
So you went on to do your PhD in Bristol.
Yeah, that's right. I finished my undergraduate in Manchester it was 2015, and from there I went down to Bristol to do my PhD in their School of Earth Sciences in cosmochemistry. So really, I really got the bug for meteoritics and cosmochemistry during my time in Manchester.
Mm-hmm.
It was actually largely thanks to Katie Joy, who sort of introduced me to the subject and helped me. One of the things that I did in my undergraduate degree that was really transformative was an internship in Houston, Texas at the Johnson Space Center.
Yeah.
And it's funny because I actually applied to do some sort of Martian project on some sort of, Martian sedimentary structures, all the dunes and all the river basins and deltas on Mars. And I actually ended up getting a meteorite project, which was really unexpected. I kind of thought, oh my gosh, I don't really know that much about meteorites. I didn't really put this on in my application, but it turned out to be the best thing that ever happened to me, which sort of sent me down the route of cosmochemistry. And it was largely thanks to Katie, I think, that I ended up getting that internship, because she used to work there with the people that I was applying for the internship with, and she really helped guide my application. Gave me lots of stellar advice on how to strengthen it, and I ended up getting it, which is great. And then I did my master's project with Katie on a meteorite, and then the rest is history.
Yeah, so I remember your master's project was on HEDs, wasn't it?
It was, yes. It was an Antarctic howardite.
Yeah.
And my project really, I had this. It's really funny, in cosmochemistry we make all these grand conclusions about sometimes the entire solar system. And entire worlds from a slither of meteorite the size of a 5-pence piece. And that was essentially what my master's project was. It was a meteorite that was found in Antarctica in 2011. I think Katie told me that it was found on Christmas Eve. So it was a Christmas Eve meteorite. And I got allocated a tiny slither of it as a thin section. And Katie just basically said, as my master's project supervisor, just go ahead and look at it with an SEM and electron probe and see what you can find. And that sort of freedom to pursue my own interests and sort of, the project was sort of like very loosely defined. But that freedom to sort of chase the interesting leads that I found with this meteorite ended up being really valuable to me and prepared me really well for a life in academic research in my PhD and afterwards.
Mm-hmm.
I think people don't realize, even with a PhD, you go in and you interview for a specific project title as such. So mine was super vague. Mine was the evolution of Mars from channel networks. What does that even mean? You know what I mean?
Well, it means the evolution of Mars through channel networks.
If I'd only known that 4 years ago, I would have passed my PhD. But yeah, but that's the beauty of it, is you do go in with this title, but then you really sculpt what the
Oh yeah.
project's going to be.
I guess that's a big part of actually doing a PhD, isn't it? It's being able
Mm.
to, develop your own ideas and then take your own path through a particular project.
I mean,
Yeah.
especially at the moment, I think a lot
Sorry,
of
go on,
PhDs are
Marissa.
going to be. I was just going to say, I think at the moment, a lot of PhD is going to be turned a bit upside down. So they're having to take quite a different path to what was being planned.
Yeah, I mean, that's a good skill, isn't it? I think to learn in general, trying to sort of adapt to particular surroundings and situations and still trying to get something, good out of it, I suppose.
Yeah, definitely. A vague sense of direction is useful for a research project, but yeah, it's something that I've learned time and time again with every project that I've been involved in, is that they always go in a different direction to what you initially anticipate. And I guess that's the nature of research, right? If you knew where it was going to go, then you wouldn't be doing it because someone would have already done it.
I mean, something that someone told me at the start of my PhD was that after you finish your project, you should always know more about the subject than your supervisor, because I guess you are the person that's at the forefront and they're just like reading a few drafts or whatever.
Yeah, that's definitely something to keep in mind.
You never feel that way, though. You always feel like, I know less than anyone else, even though you are the expert. But I think that's probably just because that's how it's a good way to think in science. You always want to be thinking you don't know enough, so you learn more about it, really. But yeah.
Yeah, absolutely. One of the things that I always do with the data that I collect now, because, after my time in Manchester, really, that I spent a lot of time using electron beam techniques like an SEM and an electron probe. And since my time in Bristol, I've spent almost all my time measuring isotope ratios on a mass spectrometer. And the precision to which we can measure isotope ratios now with these instruments is incredible. We're down to parts per million precision on some of these isotope systems. I spend an awful lot of time trying to convince myself that my data is rubbish and inaccurate. And if after a lot of effort of measuring reference materials, just double checking things, measuring things in different ways, measuring things time and time again, after much effort of not being able to convince myself that my data are rubbish, I can be kind of not sure, but more confident that it's at least good. So that sort of that doubt, I think, is core to doing any good science, I would argue, and it's probably a good thing to practice in wider society as well.
So Tim, what was your PhD project on?
Right. So as we've mentioned, so I did my master's project on a Howardite, which is the Howardites are a group of meteorites that they come from a large differentiated asteroid that experienced melting, core formation, volcanism, magmatism, brecciation, the surface of the HED parent body, which is maybe asteroid Vesta, depending on who you ask, has gone through tremendous geological change during its lifetime. But for my PhD, I went to the complete other end of the meteorite spectrum, away from the achondrites to the chondrites, specifically the unequilibrated chondrites. And so these are the meteorites that preserve the dust from which the planets and the asteroids and the comets coalesced 4.5 billion years ago as our solar system was forming. And the parent bodies of the chondritic meteorites, they did get a bit warm in some cases. Some chondrites they've been lightly toasted, but they haven't been completely destroyed by the forces of melting. Whilst some of them have been recrystallized, there are many chondrites that still really beautifully preserve the motes of dust from which the planetary bodies in the solar system coalesced. And my PhD project focused on the most pristine chondrites, the ones that didn't really experience any sort of thermal metamorphism during their time on their parent asteroid. And the beauty of these meteorites is because these motes of dust, after they coalesced, they didn't undergo much change at all on their parent asteroid. They preserve the information about our solar system from before the time the asteroids and the planets and the comets coalesced. They're the only way that we can really get our hands on pieces of the solar system as it was before the planets formed, and reworked all the material and recycled it in the forces of geology. And specifically, my PhD was looking at the chronology of these pieces of dust. It turns out that the solar system formed incredibly quickly, from the formation of the first motes of dust in the solar system until the formation of the sort of later motes of dust, it all basically happened within about a 5 million year window, which it sounds like a long time, but geologically it's not. It's practically the blink of an eye when you think about the age of the solar system. 5 million in 4.5 billion is barely anything. And so trying to unpick the chronology of that first 5 million years is challenging, but possible now because of the advent of sophisticated analytical instruments, mass spectrometers. And specifically, my PhD was involved with dating the timing, duration, and order of events in the early solar system by radioactively dating these minute motes of dust. And so that's it in a nutshell.
Were you using a range? Sorry.
No, please go on.
I was just going to ask, were you using a range of different isotopes, or was it just lead you were using?
Right. So it's kind of funny that so this is a great example of how the research project didn't actually pan out how it was initially envisaged. So the original plan for my PhD was to do lead dating and aluminium magnesium dating on the same objects. But we ended up going down a completely different path. We ended up looking at these really curious objects that we find in meteorites called refractory forsterite grains. Now, for those who are not familiar with forsterite, it's the magnesium end member of a really common mineral called olivine, which is colloquially known as peridot. It's this beautiful green semi-precious gem that's quite popular amongst the Austrian aristocracy. The Austrian equivalent of their crown jewels, these giant egg-sized lumps of peridot carved into this necklace. It's beautiful. But anyway, it turns out we find this mineral in meteorites as well. And the main thrust of my PhD then became trying to date these tiny, they're a fraction of a human hair's width, typically, these grains. Is trying to date them using the aluminium magnesium isotope chronometer. But during my PhD, in the background, we were trying to get lead dating working too. Lead is incredibly challenging to measure because there's not much lead in a meteorite, but there's loads of lead in the terrestrial atmosphere because of leaded petrol. We effectively catastrophically contaminated the entire surface of the planet with lead in the 1900s, which is not great for public health, and it's definitely not great for doing lead dating on chondrules. And,
which is what you're more concerned about.
Of course, yeah. There's any good cosmochemist worth their salt is worried about, indeed, yeah.
Yeah, absolutely. So in a nutshell, dating little bits of meteorite, it's one of those textbook figures that, the solar system and the Earth and the solar system is 4.6 billion years old. And to actually calculate that yourself and find that out for yourself is one of the best things that I've ever done in life. For many years, it's been on my bucket list to date a meteorite, and I did get to do that in my PhD, which is great.
So why did you specifically focus on these olivine grains then?
Right. So the beauty of olivine is that it's quite a simple mineral. Okay, it's really almost entirely made of just three elements: magnesium, silicon, and oxygen. And so when these olivine grains formed, they froze in their composition. So the parent isotope of the aluminium magnesium system is an isotope of aluminium called aluminium-26. Now, if you're familiar with aluminium on the Earth, which pretty much everybody is, because it's economically and industrially a really important element. My MacBook is made out of aluminium. Cans of Coke, they're made out of aluminium. All of the aluminium on the Earth is made from just one isotope. It's what we call a monoisotopic element. It's just got one isotope, and that isotope is aluminium-27. And aluminium-27 is stable. It will stick around forever. But there's another isotope of aluminium, aluminium-26, which is not stable. It's radioactive. And if you've never heard of it, there's a good reason, and that's because there's none of it left in the solar system today. It decayed long ago in the deep past of our solar system to form stable magnesium-26. Now, even though there's no aluminium-26 left in the solar system today, there was some aluminium-26 in the solar system when it formed 4.6 billion years ago. And the source of this aluminium-26 is still not quite it's not pinned down exactly where this aluminium-26 came from, but it's likely that it came from the winds of a dying star. A nearby star to where our solar system formed shed its outer layers in the latter years of its life, and these outer layers were laced with a medley of radioactive isotopes, including aluminium-26, and that aluminium-26 was mixed into our solar system, but then quickly decayed away into nothingness. And so the beauty of olivine is that it contains barely any aluminium, and by extension, it didn't really contain much aluminium-26 either. And so the magnesium isotope composition of these olivine grains hasn't changed since they formed 4.5 billion years ago. Whatever the magnesium isotope composition of these olivines were when it formed is essentially the same as what it is now that we can measure. And if you imagine when the solar system formed, there was lots of magnesium-26 kicking around. But as the aluminium-26 decayed into magnesium-26, the amount of magnesium-26 grew to its modern day levels. And so if you can measure the magnesium isotope composition of an olivine grain and see where it fits on that growth curve, you can calculate an age. And that's effectively what we did. And the beauty of the aluminium-26 chronometer lies in how fast it ticks. Okay, it ticks incredibly quickly. It's got a half-life of 700,000 years. So it was all gone. It decayed away into insignificance within a few million years. Mm-hmm. And because it ticks so quickly, it means that we can date events to really high temporal precision. It's kind of like if you imagine the time it takes to boil a kettle. If you're trying to time that using a sundial outside, you're not going to get a very precise answer because the shadow of the sundial moves so slowly. Whereas if you try and time the boiling of a kettle with a stopwatch that can go down to the level of a second, you can time it really precisely. And that's a good analogy, and it's the way that I think about these isotope systems. The faster the decay, generally the more precisely you can attain an age. So that's the beauty of the aluminium chronometer.
Mm-hmm. And what did you find? Did you find it was 4 weeks old, 6 weeks old, or?
It's 6,000 years old. The Bible was right.
Fantastic.
Yeah, you just clip that bit out of the podcast, and
that's the only part we're going to leave in.
No, so what we found was these refractory forsterite grains, they formed over an interval of about 4 million years, and that 4 million year period actually began with the crystallization of the first and oldest motes of dust, the so-called CAIs, these calcium aluminium rich inclusions. Now, these CAIs they're really funky objects that we only find in meteorites. And to the best of our understanding, and this is sort of a textbook explanation of CAIs. Of course, on the fringes of this subject, there's debate and passion from both sides, but it's fair to say that at least to a good approximation, the CAIs are the oldest objects in the solar system. In fact, the age of the solar system is defined by the age of CAIs. It's 4.567 billion years old, within a margin of error of about 160,000 years. So they actually define the age of the solar system. And what we found with these refractory forsterite grains, they began forming alongside CAIs. So the oldest refractory forsterite grain that we found, actually, it was smack bang on the age of CAIs, which was completely unexpected. We thought maybe these olivine grains formed a bit later in solar system history. Maybe there was a gap, 2 or 3 million year gap before these olivine grains started forming. But we actually found that they started forming alongside CAIs. And unlike CAIs, which all seem to have formed at the same time, CAI formation was this brief event that lasted perhaps only a few thousand years. The formation of these olivine grains was recurrent for at least 4 million years, which was not something that we expected to find at all. I remember I was sat at the mass spectrometer in Bristol. It was in the basement of the building, so it's this windowless room, and you've got the hum of the vacuum pumps and the air handling system. And I was sat at the computer, and you're seeing these numbers come through in the data acquisition program, and then dutifully pasting these numbers into my Excel spreadsheet and doing all the calculations that I'd already pre-written all the formulas just to paste the data in, and from all these numbers, and you've got a little chart recorder on the mass spectrometer, from all these numbers that don't really they mean something. You're measuring voltages on a mass spectrometer, but they don't really mean anything conceptually. You plug in these numbers, and the spreadsheet does these calculations, and out pops a number. And that number is the age of this olivine grain that you've been studying for 2 years, and out comes the number 4, 5, 6, 7 million years. And you think, oh wow, that was so worth it. 2 years of hard work to get to this stage, plugging in all these numbers into this massive body of work that you and your colleagues have been working towards, and out comes a number, and you think, gosh, that olivine grain is the oldest thing that exists in the solar system. Effectively, there's nothing quite like it.
It's also quite funny to think that you're calculating the age of the solar system using Excel as well.
Yeah, Excel I think it's vastly underrated.
Yeah.
I love a bit of Excel. There's no problem in life or cosmochemistry that cannot be, if not solved, made less of a problem by an Excel spreadsheet.
Mm-hmm.
We should just let the listeners know Tim is sponsored by Excel.
Yes, I am. No, I'm not really.
When you do these analyses, you say you need the most pristine meteorite material. How do you recognize that, in a sample and pick a sample that's going to let you ask these questions?
Right, that's a really great question. And before we even think about dating a meteorite using this particular chronometer, we have to consider two main things. The first thing is, did this meteorite experience any sort of heating during its time of residence on its parental asteroid? And there's a huge body of literature that has meticulously documented the petrographic and the chemical and the isotopic changes that a meteorite experiences on its parental asteroid. You can think of these asteroids as there's a really great paper that came out. I think it was last year or the year before in Earth and Planetary Science Letters, and it was the Munster group, and they found pretty compelling evidence using tungsten isotopes that the structure of at least some of these parental asteroids of the chondritic meteorites were shaped like an onion shell. So in the middle of these asteroids, it's quite hot, and on the exterior, it's quite cool. And then you've got everything in between. And so the most cooked, if you like, the most thermally metamorphosed meteorites come from the center of these asteroids. And these meteorites, they're almost unrecognizable as chondrites. The primary textures have been almost completely destroyed. Many of the elements have reshuffled around and evened themselves out and diffused along crystal boundaries, and it's a process called equilibration. These meteorites are really, the primary texture has been almost completely overwritten by the heat experienced in the center of their asteroid. Whereas the meteorites that originate from the very exterior of these asteroids, where they're sort of butted up against the cold exterior of outer space, they remain pristine. They weren't perturbed by heat, if at all, or at least not very much. And then, of course, you've got everything in between. And so the first thing we did with these samples, these meteorite samples, was to check, have these things experienced any sort of thermal metamorphism on their parent asteroids? Because we're trying to date things that happened in the nebula before the asteroid formed. And so if it's been perturbed on its parental asteroid, we're no longer actually dating things that happen in the nebula. We're dating things that happened on the parental asteroid. And sometimes it's actually quite difficult to tell the difference. There are lots of papers that claim they're dating things that happen in the solar nebula, but it's not so clear if you're actually dating something that happened before the asteroid formed or after, when it was perturbed by this heat. And a lot of that work was done on a scanning electron microscope, which I really like to think of as the bread and butter for a cosmochemist. Although I must say optical microscopy is underrated. I'm a big advocate of optical microscopy as well. But, a good SEM session never goes amiss. And you can often tell if a meteorite is being perturbed by heat, because you get, for example, the most pristine meteorites contain glass, really beautiful homogeneous glass. And to find glass in a meteorite is really rare. Just a little bit of heat on glass and the atoms in the glass will begin to shuffle around and snap together to form minerals. It will no longer be a formless glass. It will become organized. And so the meteorites that we looked at in my PhD contain quite a bit of glass in most cases. And so we can be pretty sure that they haven't experienced much thermal metamorphism, if any at all. And the second thing we have to consider with meteorites, and this is a problem that plagues all extraterrestrial samples, is the history of a rock that came from outer space is not squarely confined to outer space. It's not like it fell to the Earth and then nothing happened to it. Of course, we live in it's a blessing and a curse. It's a double-edged sword that we live in an oxygen-rich atmosphere, because it means we can be alive, but it also means that it ruins extraterrestrial samples. You'll know, John, even the most meticulously curated Apollo samples are full of bugs, and the telltale signs of being attacked by the Earth. And the same is true for meteorites. We have to be really careful that things like rain, oxidation, hydration of minerals, the deposition of hydrous minerals in veins from percolating water haven't affected the objects that we're trying to date. And one of the samples in my PhD was a Saharan meteorite. It was found in Northwest Africa. It's got Northwest Africa 4502. There are still pieces to buy on eBay, which is where we got our piece from. And this meteorite, like all Northwest African meteorites, has probably been sat on the surface of the Earth for a few thousand years, during which time it's undergone quite a bit of change. And for some questions that you want to answer with a meteorite, this can stop you from being able to answer them. You know, the earthly signatures, the signatures that the Earth imparts into these meteorites can swamp the extraterrestrial characteristics of a meteorite in some ways. And so, some people, they seek the most pristine meteorites, the ones that people saw falling, and then curated them straight away. But for me, it actually turns out that it's not much of a problem, which was great. It means that we have a much widely, we have much more choice of meteorite to choose from. We don't have to go for those highly curated museum samples that you beg the curator for a crumb and you get one if you're lucky. We could it opened up the whole Northwest African meteorite collection, which was great.
Mm-hmm. So once you have all these meteorites, how common are these olivines in them then? Has it been quite challenging to try and find what you need? And how much olivine material do you need to do these analyses?
That's a really great question. So it turns out that these olivines, they're actually quite common. They're very common in a group of meteorites called the CV chondrites. Mm-hmm. And the CV chondrites are famous. They were really, they're famous for a few reasons, but they were made super famous by the fall of the Allende meteorite in 1969 in Mexico, which was this at least 4-ton meteorite that fell out of the sky above Mexico just before the Apollo 11 moon rocks came back to the Earth. And it's since, it's difficult to quantify these things, but it's probably the most studied rock on the planet. And the Allende meteorite belongs to a group of meteorites called the CV chondrites. And one of the meteorites that I studied for my PhD was a CV chondrite. It was the one that we bought from eBay that came from Northwest Africa. And they're really common. You fall in over these things in CV chondrites, and they can get quite big. And by big, I mean they can get a few hundred microns across, which is a few hairs width. I do measure the thickness of my hair from time to time on the optical microscope, check for thinning. And my hair is about 100 microns across. So, a hair's width or two for these olivine grains. They're not huge by everyday standards, but for cosmochemistry, they're quite big. And it turns out you can measure the tiny amount of magnesium, which is typically a few millionths of a gram of magnesium, is plenty to measure a nice precise isotope ratio.
Are these in situ measurements that you do, or you got to crush these things up?
Right, another great question. So there are two main ways that people measure magnesium isotopes in cosmochemistry. One of the ways is in situ, using an ion probe. So this involves getting a nice polished surface of a meteorite and sticking it under a beam of usually cesium or oxygen and firing this beam at the sample, and it sputters off atoms from the surface of the sample, and you funnel those atoms into a mass spectrometer and measure its composition, which is great because you don't destroy the sample and you know exactly what you're measuring. But the downside is that it's not too precise. The uncertainty bars that we need to date a meteorite to the precision that we were dating them, you need the uncertainty bars really small. And the only way you can do that for magnesium is using a plasma source mass spectrometer. And to do this, you need to actually get the olivine grain dissolved in some acid. So it's literally a beaker with acid in it, with the magnesium dissolved in it, which is kind of bad because you've destroyed the grain in its entirety. So you have to be really careful with the petrology before you dissolve it, because if you measured something really interesting and you don't have any idea what you measured, that's not so great. And isotope people are terrible for doing this sometimes. They'll dissolve something up, measure it really nicely, find something really interesting, and then think, hang on a minute, we didn't actually stick it under an SEM before we measured it. What was it that we actually measured? And so I didn't want to fall into that trap. I was indoctrinated by Katie in the best possible sense to thoroughly petrographically characterize things before you dissolve them. And so the problem is one of the problems with my PhD, one of the big challenges that we had to face was how on earth do you get a crystal of olivine out of a thin section? Firstly, without losing it, and secondly, without contaminating it, because these olivine grains, they're sat in quite a complicated rock. And so if you accidentally sample a grain that's next to it, you've contaminated your olivine grain. And I'm so pleased with the solution that we found, because it would have delighted my 6-year-old self to no end that we actually used a laser beam to do this. A really powerful laser that we used to basically scribe an outline around these olivine grains and blast a deep trench around them. And so you can imagine we've got the nice flat thin section with the olivine in the thin section, and we blasted a moat, like a trench around the edge of the olivine grain, so it was just stuck up on its own like the turret of a castle. And then we used a really precise automated drill bit to mill it out of the thin section.
How small was this thing again?
So these things were typically 100 or 200 microns.
That's still crazy. That precision.
It's a manual job as well. The laser is automated, and they can go down to a precision of a micron. So you can really get nice outlines. But actually drilling the things out, the way that we transfer it from the thin section into a beaker to then go off to the chemistry lab was using a pipette and a droplet of water to suck the olivine grain up and then dink it in the beaker, which is a manual job. And it's really funny, because I'd spent like the best part of 2 years characterizing this suite of olivine grains. I'd looked at them on the SEM, the electron probe. I'd measured their oxygen isotope composition in situ using a SIMS. And then when it came to drilling them out, I couldn't actually see them with the naked eye. You're pipetting this water from the surface of a thin section into a beaker, and you're not actually sure if you've got the olivine grain. And then you take it off to the chemistry lab and dissolve it. And then, of course, you can't see it. You definitely can't see when it's been dissolved. And the first time that it's confirmed that you've actually got the olivine grain nicely is when you dip the straw of the mass spectrometer into the beaker, and you can see a signal on magnesium, and you think, oh, thank goodness, thank goodness, I did actually get the olivine grain. And so there's this 3-week period between sampling the olivine grain from the thin section and measuring it on the mass spectrometer, when you're doing all this chemistry on it, thinking, I could just be doing chemistry now on nothing. and so the relief and the breath of relief when you measure it on a mass spectrometer and you think, oh, phew, I've actually got some magnesium, is quite something.
Were you successful every time?
No.
You managed to
No. So the first set of samples that I did for my PhD, I milled out about 15 olivine grains, and I lost 3 of them.
Okay, that's not too bad.
Yeah,
I don't think that's too bad a success rate. And sometimes you're looking down a microscope, and you can see them under a microscope, and you're pipetting out, and you look, and there's just nothing there. Mm-hmm. You think, oh no, it's disappeared. It's probably on the floor now, and then there's nothing you can do about that. But I did another batch before Christmas. I did a batch of 12, and I only lost 1 of them. So I'm getting better.
I think if I went to ASDA with my 12 children and I only came back with 11, I'd be fine with that.
Yeah, I mean, as a percentage, that's pretty good, isn't it?
Exactly.
So,
exactly.
I'll take it.
Exactly.
Absolutely.
Yeah. And at least you've got some good blank measurements now.
yes, that's it. And one of the things that we thought long and hard about was, how do we characterize how much magnesium we accidentally add to the olivine in the form of contamination? And the way that we got around this, it was one of the stranger little avenues that I went down in my PhD. I bought a beautiful wafer of silicon from a silicon chip manufacturer. It was this beautiful single crystal of silicon. And I'd never seen pure silicon in the flesh before. And it looks like a metal. It's like this mirror polished crystal silicon, pure silicon. It was parts per million level purity. It said on the box, and I confirmed it as well. It really was part per million pure silicon. And I drilled out and lasered out pieces of this silicon and sampled them in the exact same way that I sampled my olivine grains, and processed them in absolute parallel. And then, assuming there was no magnesium in the silicon to begin with, which is a good approximation, and then measuring how much magnesium was in the silicon at the end, you can calculate really precisely how much magnesium you added in all the subsequent steps. Yep. And it turns out that even after the laser and manually pipetting these things and dissolving them and putting them through column chemistry and diluting them and, transferring beakers a few times, we only added a few nanograms of magnesium during this whole process. And when you've got at least a microgram to measure, it's a factor of 1,000 less contamination than sample, which is really great. It's basically not a problem contamination, which was a big relief, because with samples this small, you've only got a few micrograms of magnesium to measure. Even half a microgram of magnesium contamination you'd be done. You've got no chance. You're like dead. So it was a relief that consistently the contamination, which the word that we use in the business is blank, the amount of blank that we added to the sample was in the realm of the nanogram, which is basically ignorable.
Yeah, that's great.
Yeah, it was good fun.
So you're doing a postdoc at the moment, aren't you?
Yes, that's right. So I finished my PhD in Bristol last year, and I'm currently, the funding situation is complicated, but I'm basically 50-50 split between the British Geological Survey and the University of Bristol. And because you can only live in one place at a time, I chose to live in Nottingham because I lived in Bristol for 4 years, fancied a change. And so now I work it's actually the Zircon lab at the British Geological Survey. And for those who are not sure what a zircon is, it's a mineral that contains a lot of the element zirconium. But the great thing about zircon is that when it forms, it loves to suck in any uranium from its surroundings. It just loves to grab uranium and pull it into its crystal structure, while at the same time rejecting lead. And so when a zircon forms, it's got barely any lead in it, but it's got lots of uranium. And over geological time, that uranium decays into lead. And so you can measure the amount of ingrown lead in a zircon to calculate its age. And when you look at the geological timeline, and it's got all these dates on it, the boundary between the Cretaceous and the Jurassic and the Triassic, that a lot of those dates are pinned down by dating zircons. So it's a really fundamental mineral to our understanding of Earth's history. And using very similar techniques that we use to date zircons, I say we, I'm not part of that community, but using very similar techniques to the community that dates terrestrial zircons, we're dating pieces of meteorites now. It's remarkably similar. We use the same mass spectrometer, we use similar chemistries. We're rubbing shoulder by shoulder when we're not in lockdown and social distancing in the lab. And there's someone dating zircons in the lab next to me, in the hood next to me, where I'm dating meteorites. And so using the knowledge of the people who work at the BGS, using their knowledge that they used to date zircons, we've been dating little bits of meteorites using the uranium lead system, which has been really good fun. It's certainly a lot more challenging than the magnesium isotope system in my experience.
So what kind of meteorites are you working on now?
Right, so I'm still looking at chondrites, specifically unequilibrated chondrites. So these are the chondrites that didn't experience much thermal metamorphism on their parent bodies. And the chondrites, I often think of them as sedimentary rocks. They contain clasts that are all sandwiched together to form a rock. And just like sedimentary rocks on the Earth, the individual clasts of a chondrite have different geological histories. They formed in different parts of the solar system by different processes at different times. And of all the wonderful different types of clasts that we find in the chondrites, the specific ones that I'm looking at now are chondrules. And chondrules, they're the most abundant type of clasts that we find in chondrites. So these tiny little, they're generally round, but they're not always round. And when you look at them in 3D, they're spherical. They're poppy seed sized. If you imagine the crumb of seeds that you get at the bottom of a bag of a loaf of seeded bread, that's generally the size of chondrules. And we're dating chondrules using the uranium lead isotope system, which is really challenging. There's only really 2 labs in the world that do this sort of analysis. There's only one that does it routinely. And so there's a real thirst in the cosmochemistry community for more labs to start dating chondrules and other meteorites using the uranium-lead decay system.
And what's the question you're trying to answer by dating these chondrules?
Right. So one of the huge spanners in the works at the moment in cosmochemistry is that there's a very slight discrepancy between some of these different isotope chronometers. And so if you imagine there are half a dozen different chronometers that are routinely used to date the components of chondrites. So the main ones, you've got uranium lead, you've got aluminium magnesium, which you've already talked about, you've got manganese chromium. Some of them give the same answer, whereas others give different answers to the same question. And so they can't all be right. Okay, we're trying to date events using different clocks. And if these clocks are accurate, they'd be self-consistent, they'd give the same answer. But they don't always. There is some disagreement between different clocks. And so one of the big questions in cosmochemistry now is, which of these clocks are accurate? And are they even dating the same thing? That's a whole other question. And so we're trying to find the reasons why these different isotope chronometers sometimes give different answers to each other. And one of the ways of doing that is by dating the same object using different chronometers to see if they all line up, and if not, why not? And so it's a bit of an open question at the moment in cosmochemistry, because the timing of events as our solar system was forming is absolutely key to constraining models of how it all happened. For example, chondrules, no one knows how chondrules formed, yet they're the most abundant building blocks in chondritic meteorites, and by extension, they're the most abundant building blocks of planets, including the Earth. And that we don't know how they formed represents a huge gap in our knowledge of how planets formed. And the modelers, they come up with so many different amazing scenarios of how chondrules formed. And one of the major constraints on these models of chondrule formation is how old are the chondrules? And that there's some uncertainty as to how well we know the age of chondrules. It's not helpful when we're trying to constrain these models. And so in short, we're trying to at least constrain the accuracy of these different isotope chronometers, and then that will inform our models of solar system formation.
So you've been working on the postdoc for, is it a couple of years now?
So I started, it was June the 1st last year. So I guess
okay.
just over a year and a month. A year and a month and 10 days.
So how has all your lab work been affected by the lockdown?
Right. So it's been affected quite badly, actually. And I must preface this by something we were talking about in the preamble before we went live on air, that I can't complain too much because thank goodness all my family and my friends, as we're all okay by COVID. So I'm complaining about the lab work not been going ahead with a huge asterisk, saying that actually I've got off pretty lightly in this situation. But just looking at the lab work, it's been pretty badly affected, actually. We went into just before we went officially into lockdown here in the UK, people at the British Geological Survey had basically been working from home anyway for about a week up to that point, including myself. And so up until last week, I hadn't been in the lab at all since the middle of March. And for someone whose project is essentially entirely lab-based, I'd say I probably spend about 2/3 of my time in a typical week in the chemistry lab. I spend very little time at my desk often. And so that the lab was shut basically put everything on ice. And one of the last things that I did before I left the lab was write myself a little note saying exactly where I was when I put everything on ice. And that was actually really useful last week because, after almost 6 months of not being in the lab, it's quite easy to forget exactly where you were in your procedures and where all the samples were and what sample had been, what had been done to which sample. And so when I went into the lab last week, it was really useful. I was thankful to my March self for leaving me a note saying that. But, one of the things that you learn in research is that often things go wrong. I mean, a global pandemic is pretty high up on the list of bad things that can happen, but things always go wrong. And one of the one of the things that I've learned in research is that it's always useful to try and make lemonade out of lemons. And so during lockdown, I've been working from home every day, and it's in a way it's been a little bit of a blessing because it's given me quite a lot of time to write and sift through lots of old data and pull things together and plot things up. You know, that takes a lot of time often, and so I've managed to write a couple of manuscripts during lockdown, which has been really useful because, of course, publications are the currency in academia for good or bad. That's a whole other conversation. But it's been nice to be able to sit for extended periods of time and do lots of reading and lots of writing and think about my data and plot it against other people's data sets. And I don't honestly think I would have had that opportunity had we not gone into lockdown. And so from that point of view, while it's been a shame that my lab work hasn't been going on because I love being in the lab. And I mean, it's why I became a lab-based cosmochemist. It has been good because it's given me lots of time to write things and think about my data that I already had in new ways. So, you know, while it's been a shame that I haven't been in the lab, I have enjoyed lockdown on the whole, and I have got a lot done. But God, I'm glad to be back in the lab now.
Talking of writing, I suppose that's an excellent segue into the fact that you've got a book out next month.
Yes,
Smooth.
I do have a book out next month. It's predictably about meteorites, and the title of the book is Meteorite: The Stones from Outer Space That Made Our World. And it actually got sent off to the printers yesterday, and so it's officially done. There's nothing more that I can do now on the text. It's officially done. It's taken about 2 years to write it, something like that. And so that's been keeping me busy in lockdown as well. You know, I've been in the cosmochemistry game for the best part of half a decade now. I really think that for me, it all started in my third year in Manchester when I was fortunate enough to do the internship at the Johnson Space Centre, where I studied a meteorite, and it opened up this whole new world of all these different strange types of rocks that you don't normally learn about. You know, the CV chondrites and the CB chondrites and the angrites, and oh my gosh, we have meteorites from Mars and the moon, really? Like, God, I didn't know that. And we've learned all this amazing stuff about the solar system from these really strange stones that fall from outer space. And that's really been the driving force behind pretty much my entire life for the last 6 years now, since I did that internship. And during those 6 years, during my final year in Manchester, working with Katie on the Antarctic Howardite, and during my PhD, collaborating with, you know, I did my PhD at the University of Bristol, but I collaborated with the British Geological Survey and the Natural History Museum in London. I learned all this amazing stuff, and I thought, gosh, people should know about this, because everybody loves space, right? It's really easy to sell space science as a subject, and everybody loves geology as well. You know, when you tell people in the pub or while you're out hiking that you did a geology degree, their eyes light up, and humans have this natural affinity for rocks. And I think those people who don't lose it end up becoming geologists or something like that. And so cosmochemistry and meteorites is this beautiful intersection between these two vast subjects, space science and geology. I often think of it in terms of a Venn diagram. You know, you've got the circle of space science and you've got the circle of geology, and the lovely intersect in the petal-shaped area in the middle that combines them both is cosmochemistry. And so there's this innate or this widespread interest in the subject out there, and it struck me that there's not much popular science written on this subject. Like, if you go and look at biochemistry, you're absolutely spoilt for choice for the number of popular science books that are on biochemistry out there. And there seems to be another one published every month. And it's the same for things like astronomy as well, and other areas of space science and physics as well. The physicists they're well in on the game of writing popular science books and bringing their science to a public audience who perhaps are even not scientists. They might not have studied science formally since they were 16, but the only prerequisite you need to understand these books is an interest in science and a bit of time to either sit or listen to a book. So I thought,
it was kind of a similar reason we started the podcast, because we realized there's all these podcasts out there about physics, biology, but there's very little on planetary science. And obviously it's not as grandiose as starting a book, but you know.
I don't know. You know, one of the things that I think the last few years has shown us is that the spoken word probably has a wider reach than the written word. Very few people will sit down and read a book, but everybody is listening to podcasts at the moment and audiobooks. It's almost like the the Gutenberg revolution, when the printing press was invented, and it made books cheap and easy to produce, and just orders of magnitude more people had access to the written word and information and conversation and debate and discourse. Well, the same thing has happened again recently, but with the spoken word. And so I actually think podcasts and audiobooks they probably have a far wider reach than the written word, which is why next week I'm recording the audiobook version of Meteorite, which I'm really looking forward to. Apparently a Yorkshire accent doesn't preclude you from becoming an audiobook narrator these days, which is great.
Well, we'll see, won't we?
We'll see. Maybe no one will buy it. Maybe they'll all get a refund on Audible or something. And so I had this big bank of knowledge from my own research and my wider reading around cosmochemistry. And for a long time, I've been doing public lectures as well in schools and at public events and festivals. And I thought, wouldn't it be great to get this out to a readership as well? And so I sat down and wrote a book about it. And it's the first long format piece of writing that I've done for a public audience. I've done the occasional blog post and the occasional written interview, but it's really the first long form piece of writing that I've done for a general audience. And for me personally, I mean, of course, I hope that people enjoy the book, and I hope people, if I'm lucky, they'll have more questions by the end of it than answers. But for me personally, writing the book has been a really great experience as well, consolidating this vast body of literature that's been collected over really the last 200 years in cosmochemistry, and synthesizing it and making a coherent piece of text out of it and organizing that information has been wonderful. And I learned so much about particularly the history of meteoritics that I probably wouldn't have learned otherwise. And you know, I think one of the things that is often not taught to undergraduate students about writing is that writing is the best way to think, or it's one of the best ways to think. Very few people can sit down and shut their eyes and think about something, because you know your brain is competing for attention, and there's lots of things trying to grab your attention from all different directions. But sitting down and writing is a really, really great way to organize your thoughts, and this book has done that for me no end. I feel like if there's ever a cosmochemistry round at the pub quiz when lockdown gets lifted, I'll stand a pretty good chance of getting at least 8 of the 10 questions right.
Were there any particularly unusual or kind of interesting things? I mean, I guess the advice would be read the book, but things about like the history of meteoritics that you found that you just didn't expect, or?
So one of my favorite little tidbits that I found out during the book was that it's not just the minds of modern science that were fascinated by meteorites. There was a paper published in 2016 in a really popular, although admittedly basically strictly academic journal called Meteoritics and Planetary Science. A few nods, but everyone in this game is familiar with that journal, but very few people in the public read it. But some of the things that are published in that journal are wonderful. For example, there was a paper published in 2016 where some researchers went to the Egyptology Museum in Cairo and analysed the composition of the blade of King Tutankhamun's dagger, and found that it was made from an iron meteorite, which is wonderful. It's this great sort of overlap between Egyptology and archaeology and cosmochemistry. The ancient Egyptians were making sacred artifacts out of meteoritic iron thousands of years before the Iron Age, and so it really, in a kind of strange way, I don't want it to sound corny or anything, but it made me feel really sort of like connected in a way to the ancient Egyptians, thinking, gosh, here we all are, you know, me and my colleagues and my collaborators and friends over the world, we're dedicating our lives to studying these strange stones and answering these strange questions. There's an attractiveness to these stones. And the ancient Egyptians felt that in the same way. Although they didn't have modern science, they still felt something was conjured inside them. They knew these stones were important enough to make sacred objects out of them. And while we'll never know probably if the ancient Egyptians did actually know that this iron meteorite that they made this blade out of did come from outer space, it is curious that around the same time this dagger was forged, the hieroglyphic came into common use that literally translates into iron of the sky. And so perhaps they did know, or you know, part of me thinks it is possible that they found this strange metallic substance sat atop the desert in ancient Egypt. And if you find a lump of iron in the desert, where else could it have come from but the sky? So maybe they just intuitively figured out where it came from. So there's this, and there are lots of other stories like that as well, dotting the pages of human history, where meteorites have fallen and from them has sprung a whole body of legend and lore.
It's a known fact that the ancient Egyptians had an ICP-MS, isn't it? So they probably would have used that and that.
I think there's a hieroglyphic for that.
Yeah, there's a hieroglyphic of that. So they probably knew,
That's right. They knew. They figured it out.
Exactly. Probably larger error bars on it, but they probably
only marginally though.
It was the nickel isotopes. They ended up pinning down. It was Tutankhamun et al. 4,000.
That is incredible, though. So you've been thinking about writing this for a while, I imagine, and you did the program, the BBC program. Was it called Astronauts?
Yes, that's right.
Yes. And just before we go into that, were you already considering going into doing this? I can't remember what the phrase is for it, but public engagement of scientific public engagement, essentially.
So I've always had an interest in talking about science. I guess it started out sort of selfishly in a way, because I just enjoyed it so much. And when you enjoy something, you want to share it with people. It's a really natural thing. And so during my time in Manchester, again, this is what I mean by made in Manchester. Like during my second year in Manchester, I started volunteering at the Manchester Museum, which is dead opposite the School of the Earth Science Department in Manchester. It's just literally across the road. So I used to volunteer in there. And, I'd spend the odd Saturday with a table of rocks, just showing people as they came by, just in the museum with their kids maybe, or a day out as a couple or as a family or whatever. People, it seemed to me that people were interested in this sort of stuff, and I like sharing it, so I started volunteering. And during that time volunteering, I discovered that I have a little bit of a knack for explaining things that are at first quite complicated, but the way that I learn things is always by trying to simplify it as much as possible and stating things as sort of explicitly as possible for my own benefit. That's how I learn. And it's a useful tool for explaining what at first are quite complex scientific principles to the general public as well. And so I discovered I have this knack for talking to people and explaining geological principles to people in a way that's hopefully informative and accurate, but also entertaining as well. And interesting and worthwhile. It's not just a mindless body of facts that we've learned. It's actually quite interesting, and it's got real meaning behind it. And so from that volunteering position at the Manchester Museum, I started doing talks in schools and scout groups and amateur astronomy groups, and I continued doing this when I moved to Bristol in my PhD as well. And then this opportunity came along to apply to be part of this BBC Two. It's not a documentary series, but it's not reality TV either. It's somewhere in the middle. It's reality documentary called Astronauts. You Have What It Takes, where they were going to put 12 people through the rigors of astronaut selection under the watchful eye of an expert panel, including former astronaut Commander Chris Hadfield, who was made famous by playing David Bowie in space on the International Space Station, and his very impressive mustache. And I ended up getting a place on this program, and I think that was largely thanks to the communication skills that I'd gained during my undergraduate degree and my PhD in communicating science to a general audience. I really do think that was one of the cornerstones of my application, and I ended up getting a place on it. And I met so many wonderful people during Astronauts, not just the other participants and the expert panel, but the crew as well. I got to hang out with BBC people for the best part of 2 months, and I became quite good friends with some of them and quite close to some of them. And one of the higher ups in the program, a really wonderful lady called Helen Thomas, who works at the BBC. She works BBC Science. She said to me on the final day of filming, you've got a real knack for talking about your subject. Come and have coffee with me sometime in London. When life's got back to normal, before it airs and after we finished filming, come and see me and we'll have a chat. So I went to see her in London, and she suggested that I should maybe try and do more sort of science advocacy in the media. I thought that would be great. Where on earth do I start? And she suggested that I find myself an agent to find me little opportunities, little radio opportunities and podcast opportunities. And she recommended me to an agent friend of hers, who's this really wonderful woman called Sue Ryder. she's fantastic, and she really nurtured me when she became my agent and started, you know, putting little feelers out for me in the media. And then Sue and myself and the rest of her clients, we merged with a new agency called North Bank Talent, and they have it's a team of agents. There's someone who specializes in radio, in TV, in events, and there's also a literary agent. And I thought, oh, maybe I should start writing a book. You know, I've got this huge body of knowledge. Maybe it's not enough to fill a book, but it turns out it was enough to fill a book. And so I sat down and I just decided, right, I'm going to write this book, and I did. So that's kind of the story of my science advocacy, if you like. It all really did start volunteering on a Saturday afternoon in the Manchester Museum, and I can draw a direct line between doing that as an undergraduate, not really having any idea how to talk about science to a general audience, to writing this book.
So I even remember you going to the museum to do your little shifts over there and going to visit you sometimes. So it's crazy to think back to those times, yeah, and then where it's come to now, you know.
What were you doing in the meantime, Ricky?
I mean, look what I've done with my life. God.
I mean, you're on the surface of Mars.
God, working for the European Space Agency, what have I done with my life? But yeah. It's crazy. It's crazy to just look back. That's all, you know, and see how far we've come is amazing, really. You know?
And I think that's certainly one of the strengths of the cosmochemistry and the Earth Science crew in Manchester. The importance that the people in Manchester and the student, you know, everyone from the professors all the way to the undergraduates and everybody in between, there's this celebration of science and sharing it with the general public. And that's in my experience not something that all academic groups are fond of. I think there's actually sometimes a little bit of an arrogance in academia, looking down on public outreach and getting the public engaged, because, well, I don't know why exactly, but I do think it's one of the most important things that you can do as a scientist. It's definitely not a prerequisite to being a scientist. Some people have no interest in it, and some people are actually no good at it, which is fair enough. Maybe I don't know. Maybe some people like to be purely research focused, which is totally fine. But I do think it's useful in academia to have at least a large minority of people who will go out and share the science with the general public, because, you know, what's the point in doing science if you're not going to share it with anybody? And so that philosophy in Manchester of sharing the science is something that's definitely stuck with me. I picked it up in Manchester.
And also, I suppose, ultimately, a lot of our research is funded by the public too. So, I mean, it's only right that we should be able to then give all what we're learning back to who is ultimately funding us.
Absolutely. I completely agree. Yeah, definitely.
Because at the end of the day, if we publish a paper, there's only certain people who are going to read it, and they're unlikely to be members of the general public. Yeah. So, yeah, you're definitely right.
While it's open access, no one's going to read it.
Yeah.
Yeah, absolutely. And even if it is open access, people generally don't read the academic papers anyway, because you need a degree level background knowledge to even understand most of these papers. Even papers within my own field, I have to sit down and really dedicate a good amount of time to understanding them. Yeah. And it's not just from a funding perspective either why it's important for the public to have at least an appreciation of science. I think it's also really important to any well-functioning society, any sort of democratic society, to have a good understanding of science, because arguably our civilization is built upon the fruits of science. You know, we live in a technological civilization which was born out of the scientific mindset, and to have a society built on something that nobody understands is precarious at best, and I think foolish would be a good way to characterize that. And so even if I'm not saying that everybody should become scientists. God, no, I'm not saying everybody should become scientists. But I think having more of an understanding of the scientific mindset and the scientific process in society can only be a good thing for a well-functioning democracy.
I was watching a documentary about Armenia, and I'm generalizing based on what they said in the documentary, but essentially the way their society was run, they were taught at school, it was almost cool to be into science, and what they wanted the next generations to be after the Armenian genocide about 100 years ago was a culture of science. And I just thought that would be amazing if that was what the UK was. If we were a culture of science, we were brought up thinking science is a really cool thing. As you say, not to necessarily go into it, but at least have the mindset in that way.
Yeah, I couldn't agree more. And I think that the appetite is there. If we've learned one thing in the last 10 years, it's that people are way smarter than we give them credit for. You know, we've basically, since the advent of television and radio, we've been confined to forms of media that are incredibly narrow bandwidth. You know, adverts, the average length of an advert has gone down by several factors over the last few decades. Things are delivered in sound bites. TV programs, if you're really good, you'll get an hour on BBC4, and you know, these are not really enough time to explore complex situations in any sort of depth.
Yeah.
And it's the same with radio as well. If you're really good, you'll get a 4-minute slot where you can talk about something, but again, it's not enough time to go into any sort of detail. And if you know, this internet revolution that's happened, I mean, it started before the last decade, but certainly in the last 10 years, when basically everyone's got internet everywhere at any time. And it's given people like yourselves unlimited bandwidth to talk with people for any length of time. And people can listen to it on YouTube and their favorite podcast players and share it on social media. There's a real appetite for long form discussion out there. And it's essentially free to make as well. It's like this huge democratization of media. And God, while television viewership is going down, podcast views are going up. And a lot of these podcasts, they're 3-hour conversations on quite meaty subjects, quite intellectual subjects, yet they're getting hundreds of millions of downloads a month in some cases. There's a real appetite out there in the public for in-depth, intelligent discussion. And it's great that podcasts like this are really capitalizing on that and getting out to a wide viewership, because there's a real appetite for it. And so this gives me hope that it proves to me beyond any sort of reasonable doubt that people are way smarter than we give them credit for, and there's a real appetite for in-depth discussion out there. And if scientists can move into that field as well, society would be all the better for it.
Yeah, definitely. And it's wonderful to see you going out there and going, look, this is what planetary geology is. Have you found it, as we said before, there's lots of popular physics books, lots of popular biology books and TV shows. Have you found it harder to communicate planetary science to people when there really isn't much popular science out there already on the subject?
So we kind of we start the race a few steps ahead in planetary science, because people are already interested in space science and people are already interested in geology. And for me, the way that I like to talk about cosmochemistry and planetary science is to use things that are pretty already well known in the public sphere, but put them together in a way that perhaps people haven't thought about, but are things that people like us think about all the time. A nice example of this is there's a long chapter in my book about nuclear synthesis and the link between nuclear synthesis and the composition of the solar system, you know, the composition of a rock. And so, you know, nuclear synthesis is something that I think is, maybe it's not fair to say it's in the mainstream public consciousness, but people are talking about nuclear synthesis now a lot more than they did 10 years ago, thanks to, you know, documentary series and popular science books and sciencey podcasts. And cosmochemistry can add a new perspective to this subject by talking about the link between nuclear synthesis and meteorites. We find components in meteorites, little tiny crystals, tiny rocks essentially, that contain the isotopic signatures of different types of nuclear synthesis. And so by studying meteorites, we can actually get our hands on real pieces of stardust, little bits of dust that crystallized in the winds of dying stars that were blown into our solar system. They got caught up in the coalescing of the asteroids and the planets, and we can find them today, meteorites. And putting nuclear synthesis in those terms, for example, for me anyway, it makes it a lot more tangible than talking about nuclear reactions that's happening in that speck of light up there that is literally just a speck of light, even through a really powerful telescope, that we can study nuclear synthesis down a microscope in a rock that you can see in a meteorite. Although you need a powerful microscope to see these things because they're generally less than a micron across. But that you can study nuclear synthesis in the lab and hold pieces of stardust in a rock in your hand is a lot more tangible to people, I think, than talking about wavelengths of light coming from a star or modeling the interior of a star. And so, you know, one of my favorite things about planetary science is it's so innovative and it comes at these questions from different perspectives. You know, I have colleagues and friends who study these grains that came from dying stars. And they're geologists by training. They're not astrophysicists. They're not physicists. They're geologists. And here they are getting on the game of nucleosynthesis. It's one of the great things about planetary science is that it comes to these long-standing subjects in science from a different perspective. And that's something that I always try and do in planetary science is to show sort of how innovative it is and how it can come at these questions of science from different angles. And it's something that I try to do in my book a lot as well.
I think it says a lot about the kind of accessibility of some of this material, that even now, when I try and recommend reading about this kind of things to people, I always have to go back to the 2 chapters in A Short History of Nearly Everything by Bill Bryson, which covers the solar system and the Earth. So, I'm excited to have another resource to point people to that hopefully does a good job of summarizing everything.
I love that you mentioned that book, 'cause it was one of the first popular science books that I ever read in high school.
Actually.
My supply teacher in year 7 science recommended it to me, and I remember she wrote it down in my planner, Short History of Nearly Everything, Bill Bryson, and I went home and bought a copy from W.H. Smith's back in the day. It was one of the first popular science books I read. And another reason that I wrote Meteorite was that if in 15 years' time there are a group of PhD students and postdocs talking about, I read this book called Meteorite, and it sort of got me interested in this sort of thing, then gosh, those thousands of hours of writing the book will have been worth it 1,000,000 times over. Because I'm really grateful that I had scientist role models growing up. The likes of Bill Bryson's not a scientist, but he's a science popularizer. The likes of Bill Bryson writing about these subjects. Carolyn Porco, who was on the Cassini imaging team, which is just one of the most beautiful missions, I think. Stephen Hawking writing popular science books. Carl Sagan, of course, just a beautiful writer, really influenced me as a younger person. And so if I could be that to at least a few people, that would be amazing. It would make writing the book even more worthwhile.
That's something I think is really beautiful about doing something like that, doing a book like this, and public outreach in general, and speaking to the public about science and making it something they can understand, especially if someone can read your book and understand it as a child or young teenager. It makes them think. It goes back to this thing of we don't give people enough credit of how clever they really are, and I think that reflects in that people don't give themselves enough credit. But if they read something, they go, I understand this. They will then come to university and go, you know what, I actually do already understand this type of stuff. I can do it,
Yeah, absolutely. It raises people's expectations of themselves when you give them an opportunity to understand something complicated, because the world is a complicated place. Okay. And tweets are great, but they don't solve anything. To really understand and solve a problem, it requires a lot of study and a lot of understanding of lots of different areas and synthesizing it to produce a solution to a problem. And so I think by giving people, whether you go to university or not, giving people an opportunity to understand a subject raises their own expectations of themselves. I remember reading The Selfish Gene by Richard Dawkins a few years ago, and I haven't studied biology since I was 16 years old, and it was quite a difficult read for me for that reason. But by the end of it, I kind of got it. I kind of got the fundamentals of the evolution of life, and I thought, God, I did a pretty good job of understanding that. Maybe I can now go read another book about something that I don't know about. And so yeah, giving the people an opportunity to understand something that's quite complicated just raises people's expectations of themselves, and there's nothing bad that can come out of people having a higher expectation of their own abilities than what they did before.
Well, I'm just looking at the time, and I think that's probably a great place to come to the end. I don't know what you guys are thinking.
Yes, unless there's any other questions people wanted to ask, I'm happy to ask the final question.
Yeah, I guess
I'll just show you really quickly before we wrap up. My book Meteorite was sent off to the printers yesterday, but my publisher sent me a draft of the front copy of the book a few weeks ago, and before I saw this, my book was a text file on my computer. It didn't really seem real, but this made it seem all the more tangible.
Fantastic.
And it's very beautiful, and it captures the spirit of the book.
It's out in August.
That's right. It's available to pre-order now, and it's out in the middle of August in the UK, the US later this year. and
Fantastic.
internationally at
I'll
another
put a
date.
link to some sort of vendor in the episode description.
Cool. And I had no part to play in designing the book cover, so I'm allowed to say it's beautiful. I
Yeah,
hope
it is
the
beautiful,
outside is
though.
as good as the
Yeah.
outside.
Yeah.
So there we go.
Amazing, lovely, thank you. Well, a question that we ask all of our guests as the final question is, if you could be doing something completely different as a career, either inside of academia or outside of it, what would you want to do?
If I had unlimited money and unlimited lifetimes, I would probably become a hiking guide in northwest Scotland and take people on geology hikes. So an extended scientific presentation over the course of a full day while walking to the top of a mountain. And
That sounds
down it.
great.
Because, although I've sort of dedicated my life to meteorites, what's true for meteorites is true for anything in the world. The more you know about it, the more interesting it becomes. And one of the things that attracted me to geology so much as a 4-year-old, and still does now, is that the more you know about a landscape, the more beautiful it becomes. The aesthetics of a landscape are available to everybody, but the deep time and the geological processes that have gone into crafting that landscape are accessible to people with a geological mindset. And so knowing more about something makes it more beautiful. And I think geology really encapsulates that philosophy really nicely. So I'd become a hiking guide and do geology tours of the Highlands.
Aww.
It's just a real shame you're not allowed back in Scotland, isn't it? But
It's a real shame, yeah.
Other than that, it's a great idea. Yeah. So I think we should just say thank you so much, Tim, for coming on. It's been great.
Thank you.
Well, no, thank you. And yeah, do feel free to come back on very soon, and we can catch up with you again.
Thank you. I'd love to.
Your lab escapades. But also, thank you all to the audience. If you want more Earth and Solar System content, do check us out on social media everywhere, from Twitter to Facebook to Instagram. We're at Earth Solar System. All the links will be in the episode description. But until then, have a lovely week, and we'll see you all next time. Bye-bye.
Bye.